Good morning, everyone. Thank you for joining us on this morning's webinar on building an analog totalizer. We'll just go through the usual routine. We'll get straight into the presentation, and if you have any questions, feel free to put them in at any point, and we'll have a look at them at the end.
Hello and welcome to today's webinar. Let's get started. Let's look at our agenda for today. Today we're looking at how to build an analog totalizer with the Horner OCS. We'll start by reviewing what an analog totalizer is and when it is used. We'll look at the key design considerations you need, for example, measuring elapsed time accurately and having accurate analog readings. We'll talk about how we might need to design the logic to do analog totalizing in the OCS, and then we'll look at a previously created user-defined function block that could be used for a future analog totalizer application. So an analog totalizer is an electronic device that is usually used in conjunction with an analog flow meter or an analog flow transmitter. It's used to totalize how much flow is coming out of that sensor. So, for example, if you have a flow transmitter whose output is scaled in gallons per minute, then the totalizer is going to indicate the total number of gallons of flow. Now, the pulse totalizer is a more common application and is an alternative to an analog totalizer. It's a counter that can scale the input. For example, if you have a flow transmitter, but instead of that flow transmitter putting out an analog signal, it might put out a pulse train or a certain number of pulses per gallon of flow. A pulse totalizer is quite a bit easier to apply than an analog totalizer because it must just count the pulses and multiply by the scaling factor. There are a few benefits to analog totalizing with an OCS. Firstly, if you eliminate the need for a separate instrument to totalize the flow, by having that function built into the OCS, you can utilize the logic control capability, the data logging capability, and the OCS alarming if the flow goes above or below a certain level, and you can also get the totalizer onto an industrial communication network, like Ethernet IP or Modbus TCP. Now we look at how analog totalizers work. On this chart, we can see the flow rate graphed on the y-axis and time on the x-axis. The blue curved line indicates the flow, so it's flow rate versus time. The job of the analog totalizer is to calculate the area under the curved line, which then gives us the total flow. The easiest way to do that is to take periodic analog samples, which are flow rate samples, and create a slice that we can calculate the area of, and to get the total area under the curve, we take the area of each individual slice and sum them up. And that's the total flow. In terms of area calculation, we can see that the area of the slice we want to measure is effectively a trapezoid. So to calculate that area, we take the average flow over the start and end of that sample times the amount of elapsed time in that sample, and that will give us the area under the curve for that slice. The basic function of the OCS-based analog totalizer is the following. We measure an analog signal from a flow meter that could represent gallons per minute. We measure the incremental time between analog samples, and for that one we need to ensure it's an accurate result. Then we calculate the incremental flow by doing the maths for the area under the curve of that individual slice, and then we sum up the incremental flows, which are the individual slices, to create the new flow. So any OCS could be an effective analog totalizer. It just depends on your application and how important it is that you get the utmost accuracy. If you are measuring coolant, for example, and you do not need perfect accuracy, then any OCS will work. But if you're looking to do it in the best way possible, you will want an analog signal that updates each scan and has sufficient resolution and accuracy for your application. So, the more demanding the application, the higher the specification you will need. When it comes to measuring incremental time, all OCS models have similar capabilities for measuring it, so it's not as big of a factor. Although, picking an OCS model that has slightly faster scan time can be advantageous in certain situations. So for the example today, we would recommend an XL4 with Model 5 built-in I/O, because as the analog I/O is built in, the analog samples that we're going to be taking over our flow meter will be happening every scan, and that's going to keep our analog samples synchronized with our scan rate. Also, the Model 5 built-in I/O has 14-bit resolution, and the XL4 and the XL4 Prime both have a fast scan rate. Now, plenty of other OCS models would work well. If you have an application where the accuracy isn't as critical, then a micro OCS with its 12-bit built-in analog would be fine. So now we'll look again at what today's main focus is, taking analog samples, keeping track of our time, and calculating the area under the curve to get the total flow. So this is what we're going to do on each scan in our application. Firstly, we'll calculate the scan time, how long it's been since the top of the previous scan. This is important because we take our analog samples from our flow meter at the top of every scan, so we need to know how long it's been since the previous. Then we'll look at our current reading from our flow meter and compare that against the previous reading from the flow meter. And using those two values, we're going to calculate the average flow rate over the past scan, which is important for calculating the area under the curve. And then we'll calculate that area under the curve. and that's our incremental flow. And then, once we've calculated the incremental flow for this scan, we're going to add it to an accumulator, which will give us our total scan as we go. There's a 10 millisecond, 100 millisecond, and 1 second tick available in Cscape when you're configuring your OCS or where you're programming your program, which could also be used, but there can be some variations based on scan rate, so in an application where you're trying to accurately calculate volume, those inaccuracies can make a difference over time. So today we won't use the ticks as our indicator of time, instead we'll calculate the scan rate of every scan. To do that, we're going to need a really accurate time source, and the most accurate time source available on the OCS is a 10 MHz clock that's built into the OCS high-speed counter capability. So you can go into high-speed counter configuration and you can configure the high-speed counter to have a totalizer using the internal 10 MHz clock. And so you'll end up having an analog input register that's double integer in size, which will be continuously incrementing in 0.1 microsecond increments. And by comparing the value in that accumulator between scans, you can accurately determine what the elapsed time has been since the last scan. That calculation of time isn't difficult. We look at the accumulator this scan and compare with the accumulator last scan and subtract the two, and that gives us our elapsed time in 1/10 of a microsecond increments. However, we must be aware that the accumulator can go up to a large value and then it will eventually roll over. So the way we can tell if it's rolled over or not is just by checking to see if our current reading is greater than our previous reading. If it is, we do the simple subtraction. If it's not, we must do a little bit more of an involved calculation, which you can see there on the right. Now that we've calculated our elapsed time, we need to calculate our average flow rate. For that, we look at our analog reading this scan, add it to the analog reading of the previous scan, and divide by 2, and that's the average flow rate. Calculating the incremental flow is the area under the curve of that trapezoid, which is our average flow rate that we just calculated multiplied by the scan time that we also calculated earlier, and that gives us our incremental flow. So next is just adding the incremental flow to an accumulator and keeping track of our total flow. So now we'll have our first demonstration. So here's our program. First, it requires that we configure the high-speed counter, so we'll go to the hardware configuration and go under local I/O. In this example, we've used a Model 2, but again, if you have an application where you're looking to do this as a primary part of the application, the Model 5 might be a better choice as it offers more analog resolution. So now we go to configuration and then module setup. And then under digital inputs in high-speed counter, we make sure we set one of the counters to totalizer with the internal mode of the internal clock 10 MHz. So by configuring it like this, we know that we have an analog input register, a double integer register, that will be continuously incrementing that we can use to compare and calculate elapsed time. So that's the configuration requirement for this example. Now we'll look at the logic. We started out by looking at the current reading in the high-speed counter accumulator, which is counting at a 10 MHz rate. And then we also take note of the analog input value from our flow meter for use later, and we'll call this analog input now. For the analog reading, it's immediately converted from an integer to a long real, which is a double precision floating point value. We do that because when you're calculating flow, you don't want to have any round-off errors. So we use the highest precision maths possible to eliminate that risk as we're calculating our incremental flow and then eventually calculating our total flow. Now that we've looked at our current readings of time and analog, now we'll calculate our elapsed time. So when we calculate our elapsed time, it's usually just subtraction, the time now versus the time previously, and we subtract it. However, we must check and see if there's been a rollover or not. That's what this less than instruction is doing. If there's a rollover, a flag will turn on. If the rollover has not occurred, we can do the subtraction. If the rollover has occurred, then we need to do a more complex calculation. What we'll do is, we'll take the previous reading that we had, subtract it from the maximum value that the accumulator can accrue, and then take that difference and add it to our current reading. And then that will give us our incremental scan rate. Once we've calculated elapsed time, then we calculate our average analog reading by taking the reading from the previous scan plus the reading of the current scan, dividing that by 2, and then that gives us our average reading. The next thing we're going to do makes scaling easier for multiple applications. This is allowing, as an input to the application, for our application program to specify what are the minimum and maximum values of our analog input, and these are in counts. So, with a typical OCS analog input, if you've got it configured for 4 to 20 milliamps, the minimum analog input value will be 0 and the maximum will be 32,000. So, we'll perform some scaling here. So we take the analog input value that's scaled from 0 to 32,000 and the average reading that we just calculated up here, and then we scale that to between 0 and 1 to create a unit volume. The reason we do this is, for example, if you have an application where full scale for that flow meter is 100 or 1000 gallons per minute, or 0.1 gallons per minute, etc., by scaling the readings in a unit fashion, it's going to make it easier to scale it later to engineering units. Once we've got elapsed time and we've got average analog reading, then we multiply those two together and we get a result of the area under the curve. Here we need to make sure all our units match, and that the units of time that are coming from that accumulator register in the high-speed counter are coming back in terms of 10 million counts per second. So if we want to get our volume in gallons per minute, we're going to have to get from 1/10 of a microsecond increments to seconds, and then from seconds to minutes. So that's what we'll do here, dividing it by 10 million to get to seconds, and dividing it by 60 to get to minutes. Next, we make sure that the value we just calculated is not negative, because we never want to see a negative flow. When you have an analog input that is going from 4 to 20 milliamps and it comes into the OCS, there's the risk that the value could go slightly below 4 milliamps and it could be slightly negative. And then we would be subtracting off flow, which we should never do. So this one rung is just used to make sure that we never end up with a negative result from our calculation. Finally, we're just going to sum up the total volume by taking the area calculation that we just made of our time slice and adding it to an accumulator of the previous ones. We also provide a means to clear our accumulator out, and then the last thing we do is we scale our unit accumulator to engineering units, minimum and maximum. So the minimum might be 0 gallons per minute and the maximum might be 1000 gallons per minute. And then, at the end of the scan, we must store away our current time reading from our high-speed counter and our current analog reading from our analog input, because that's what we're going to compare against the top of the next scan. So that's what's involved in doing analog totalizing within OCS. Now we'll look at an example. What we see here is our scan time calculation, our flow which is coming in from a flow meter that is simulated with an analog input here. And currently, the totalizer is not enabled, because in theory there's no flow right now. Now we'll look at another screen to see our engineering unit scaling. So, from 0 to 32,000 counts in our analog input, we're saying that correlates to 0 to 10 gallons per minute. Now we'll enable totalizing and get the flow moving. And you can see that the flow average is around 5 gallons per minute. And our total flow accumulator is moving up, totalizing and counting the total gallons of water in the application. So that's what's involved in doing analog totalizing with an OCS. The next thing we'll look at is taking a user-defined function block and utilizing that instead of doing the logic programming. To make things easier, we've created a user-defined function block that allows you to just drop into your application without going to all the effort of creating one. So let's get back to Seascape. We'll create a new application and make it variable-based advanced ladder, because that's what we need to be able to use user-defined function blocks. Under logic modules, we right-click and press import logic module. Then we type in star.cpu so that Seascape can find the previously created UDFB, which is called ALG_TOT. And because it's not protected, we can see the logic inside. Now we'll go to the main loop and add a UDFB to our program. But first, we go into hardware configuration and make sure that we've created a high-speed counter using internal totalizing of the 10 MHz clock. So we go to local I/O and go to the high-speed counter setup. For one of these counters, we'll do totalizing, and by default, it's set for internal mode with the internal clock of 10 MHz. So that's all to enable capability in the OCS. Now we'll add that UDFB to our logic. So we'll do an always-on contact here, create a new rung, and drop in this UDFB. When we drop in a UDFB, we must give it an instance name. So what we're doing here is we're measuring the volume or the number of gallons of water in our flow application. So we'll name this instance gallons of H2O. Now we need to name all these variables, the inputs and the outputs to and from our UDFB. So we'll start with an enable, which in the case of this user-defined function block, when that's on, totalizing will happen. In other words, we'll keep adding to our total. When that's off, we've prevented the totalizing from incrementing. So we'll create a signal called enable. Next is a signal that we need to get from our high-speed counter. That's the 10 MHz clock. So I'm going to call this HSC 10 MHz. This one is the way we can clear our totalizer if we ever need to. So we'll assign a variable called clear push button here. And then this is the variable that's tied to the add analog signal from our flow meter in the case of a liquid flow application. So we'll call it flow AI. And then this is the minimum value of our analog input, which we'll say is 0. So minimum and maximum are 0 to 32,000. For engineering units, we'll say it is 0 gallons per minute to 100 gallons per minute. That's our scaling. And then output is going to be the accumulated volume of water in this case. So we'll name it total gallon of water. And then this is just a status of the UDFB, which we'll call gallon H2O status. Now when we press OK, because we've created all these variables on the spot, one by one Cscape is going to come up and prompt us to fill in all the details of these variables. So let's start that process now. So we press OK, it's telling us enable does not exist and asks if we want to create the variable. So a Boolean global variable named enable is fine. The next one is the high speed counter 10 MHz variable, which we need to make sure is an unsigned double integer, which it is, but we also need to map it to the high speed counter accumulator that's at AI 401. So we'll do that now. It says the clear push button does not exist either, so we create it. Again, global boolean is fine. Flow AI is the signal from our flow meter, and this is signed because the data could come back negative depending on if it's a little below range. So we don't want to make that unsigned, we'll make it an integer. And then we map it to the appropriate analog input. So let's say it's analog input 1 where that flow meter is wired. And then the same with total gallons. What's important here is that for total gallons, we selected in the UDFB that this is not a boolean but a long real value. So we need to make sure that a long real is selected here too. And then it asks for the status variable, which will make an integer as well. And global is alright, so we're done. This is all that needs doing when using a UDFB that's already been created. There are lots of benefits to UDFBs, and it's especially easy when they've already been created. So that's the end of the demo for today. Analog totalizers are more challenging to apply and more prone to error than pulse totalizers. The reason being, with analog totalizers, we must accurately measure analog and time, and then we must do a lot of calculations and keep track of a total. Whereas with a pulse totalizer, we simply count pulses and multiply by a scaling factor. However, there are certainly applications where you need to do an analog totalizing, and pulse totalizing is not an option. When you're using an OCS as an analog totalizer, you should use a unit that has built-in analog, because then you know your analog readings are going to be synchronized with your time calculations. For most accurate time calculations, make use of the 10 MHz clock that's built into the high-speed counter capability. And then, if you have an application like this in the future and you'd rather just use this user-defined function block instead of creating your own logic, we're going to post this UDFB online where you can access it and use it anytime you like. So that concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, so that's the presentation done. We just had one question and someone was having issues with seeing it. So if anyone else had any issues, please let us know if it's not just a single case. But in that case, as these webinars are uploaded after each one, so you can go back and look at them. For next week then, it is a Cscape drum sequencer using UDFB. So the registration link is up and available to register now. It's the same time every day, every week. Okay, thank you all for joining us this morning. I think that's it. We hope to see you again next week. Have a good day.